Okay, now that we know how the basis of caches work and what makes them work, which is locality, let's look how we put a bunch of caches together to form what we call a hierarchy. But before we get there, let's just stop to think a little bit about the cost of cache misses. The difference in time cost of a hit and a miss is huge. It could be 100x. That means that a hit can be 100 times faster than a miss. And just to make you see this in numbers, would you believe if I told you that a 99% hit is twice as good as a 97% hit in terms of time? And in this example here, let me show you. We say that a cache hit costs 1 cycle, and the penalty of taking a cache miss is 100 cycles. Okay, it means that the average access time for 97% hit rate is 1 cycle, which you always take the hit. You always take the hit time plus 3% of the time. You're going to pay 100 cycles, which is your penalty. That leads to a 4 cycle average cost. But now, if you look at this number for 99%, that'll be 1 cycle for just the hit time, to determine whether it's there or not, plus 1% of the time you're going to pay 100 cycles. So that means that the average cycle is 2. There's a 2x difference in average access time when you go from 97% hit rate to 99% hit rate. That's why we often use miss rate more often than we use hit rate. Okay, so now let's just look at the basic concepts of cache performance metrics. Okay, the first one is called the miss rate. Okay, and the miss rate is a fraction of memory references that are not found in the cache. Okay, that's 1 minus the hit rate. Okay, so the hit rate is the percentage of accesses that hit in the cache. So 1 minus the hit rate is what we call the miss rate, which is the fraction of accesses that do not hit in the cache. Okay, and the typical numbers that we see for the first level of cache, which is the level of cache closer to the processor, we'll see what that means in more detail in a second. But for L1, the one that's closer to the processor, the typical number is between 3 and 10%. Okay. Now, the hit time is the time it takes to deliver a cache line the time it takes to deliver a cache line that's in the cache to the processor so it can consume the data. Okay, and that also includes the time to determine whether the line is in the cache or not. That's why in the previous example we included the hit time even when computing the overall miss penalty. Okay, so now the typical hit times for L1 is between 1 and 2 processor cycles. That means that the L1 cache is very, very fast. Okay. Now the miss penalty is the time you pay when you do have a cache miss and you have to go to the lower levels of memory to bring the data. Okay, and that varies between 50 and 200 cycles. Okay, so that's why I said before, remember there was about a 100x difference between a hit and a miss. Well, here's an example. Okay. So there's something that we call a memory hierarchy, which is putting a bunch of types of memory together, a bunch of levels of memory together. And the reason this is good is that almost always when you have faster and smaller memories typically mean faster. They're also more expensive. Okay, so that means that suggests why not put a little bit of fast, expensive memory closer to the processor, backed up by a little bigger memory that's cheaper and a little slower, and compose that all the way down to the disk even. Okay, so and this is profitable. This is good because there are gaps between memory technologies, and these gaps are widening. Okay, that's true. If you look at the performance of registers versus caches, that's widening. Okay, as with new processor generations, and so is the gap between cache performance and DRAM performance. Okay, and then also between DRAM and disk, and so on. Okay, and if well-written programs exhibit locality, that suggests that you can actually build progressively larger and slower memory hierarchies and still give the illusion, from the processor point of view, that the memory is most of the time pretty fast. Okay, so these properties really complement each other beautifully to form a large pool of memory that behave as if it were very, very fast, even though it's composed to a large extent by slow, large memory. Okay, so they really suggest organizing them in the form of a hierarchy. Okay, by that I mean we have 1, memory, backed by another memory, backed by another memory, and so on. Okay? So, and here's another way of looking at it. The fundamental idea with a memory hierarchy is that for each level K of the hierarchy serves as a cache for the level below. And the level below is typically larger, slower, and cheaper as well. Okay? Well, why do they work? Because what I just said before, because of locality. Programs tend to access data that's at level K much more often than level K plus 1. Okay? Therefore, the storage at level K plus 1 can be slower, therefore larger and cheap, and also cheaper per bit. So again, repeating myself, the big idea of memory hierarchy is to create a really large pool of storage that costs as much as the cheap storage near the bottom, okay? But serves data to the program mostly by the upper levels, which is faster. Okay, so you can create the illusion of a large pool of memory that is fast and cheap. Okay? So let me give you an example. So here's an example of memory hierarchy. At the top of the hierarchy are registers, which, as we saw before, they're different than caches because software has to use them explicitly, whereas memory caches typically are used for all caches that you care to know about work automatically. Okay, so this is the register at the top. The CPU is right here. Okay, then you have registers inside the CPU. Okay, and then right very close to the processor we have what we call the L1 cache. That's backed by a L2 cache. Some cases on chip, some cases off chip. Let me call it right on or off chip. Okay, that's backed up by main memory made of DRAM. That's backed up by disks in case you have virtual memory, which we're going to see later in this course. And you can even imagine this being backed up by caches that are in the network that go beyond your machine. Okay? And in fact, chances are that you guys also have file caches and you have caches web servers and so on. Okay? Great. So now one more example. Let's look at the cache hierarchy of the Intel Core i7, which I'm sure many of you have. Okay? So the Core i7 has, for each core inside this multi-core processor, of course it has registers, but it has an L1 cache for data and an L1 cache for instructions, and it has a unified L1 cache per core. Okay, and then there is a unified L3 cache shared by all cores in the system. Okay, so now just inside the chip itself, it has multiple cores. There's already 3 levels of cache: L1, L2, and L3. See you soon.